Hello, my name is Divya Pradeep Bendi and I will be presenting the paper called Smart Auth User-Centered Authorization for the Internet of Things for the summer 2019 semester at Georgia Tech for Introduction to Cyber Physical System Security course. I would like to acknowledge the authors of this paper, Yuan Tian, Zhanzheng Yu, Patrick Teague, all from Carnegie Mellon University, and then Nan Zhang, Xiaofeng Wang from Indiana University, Blaise Here from University of Chicago, and Ye Sun Lin from Samsung. This paper was published on the 26th Usenix Security Symposium that was held in August 2017 in Vancouver, Canada. Web URL of the actual paper has been provided below if anyone is interested. Our presentation today is going to start with an introduction and background of IoT systems. We will then discuss about security challenges faced by IoT applications today and what would be the goals for mitigating the threats. We would then introduce Smart Auth, a security mechanism for IoT apps, followed by its evaluation and conclusion. The rapid progress of Internet of Things technologies has led to a new era of home automation, with numerous smart home devices appearing on the market. Prominent examples include Samsung SmartThings, Google's Weave, Apple HomeKit, etc. These systems use cloud frameworks to integrate numerous home IoT devices ranging from sensors to large digital appliances and enable complicated operations across devices to be performed using a set of applications. Such an application, called a smart app in SmartThings, or generally an IoT app, is instantiated in the cloud. A user interface component on the user's smartphone enables monitoring and management. Like mobile apps, IoT apps are distributed through app stores which accept third-party developers' apps as well to control a home automation ecosystem. IoT apps written by third-party developers can also get access to the status of sensors and control devices within a user's home environment. Such access provides the basic building blocks of functionality to help users manage their home. For example, turning on a heater only when the temperature falls below the set point. Current IoT platforms use capabilities to describe app functionality and request access control and authorization decisions from the users. Unlike permissions, capability schemes are not designed for security, but rather for device functionality. A smart lighting application, for example, would have capabilities to read or control the light switch, light level, and battery level. Due to complexity, capabilities in home automation platforms are often coarse-grained. One capability might allow an app to check several device attributes or issue a variety of commands. This functionality-oriented design creates potential privacy risks, as granting an app a capability for device allows it to access all aspects of the device's status and fully control the device. A recent study on Samsung SmartThings brought to light security risks of such IoT apps, largely caused by inadequate protection. Most concerning is the overprivilege problem in smart app authorization. Each smart app asks for a set of capabilities, and the user must choose the IoT devices to perform the respective functions. An example is shown in Figure 1. In mapping capabilities to devices, the user allows the IoT app to perform the set of operations defined by those capabilities based on event triggers. For example, turn on a light when the room becomes dark. Unlock the door when a valid motion is detected near the door. However, this implicit authorization suffers from issues related to coarse granularity and context ignorance, namely that an app given any capability of a device is automatically granted unlimited access to the whole device. In addition to the overprivilege that results from conflating all capabilities of a single device, malicious IoT apps can overprivilege themselves by requesting unneeded and sometimes dangerous permissions. While asking users to authorize third-party apps, access to IoT devices would seem to prevent this sort of overprivileging. Prior work on permission systems for mobile apps has repeatedly documented that users often fail to act based on or even understand these permission screens. Even worse, unlike the Android permission model, which asks the user for permission to access specific resources on a single device, access control in a smart home system is much more complicated. The policy applies across devices, defining the operations of certain devices in certain scenarios based on observations of other devices. For example, ring the bell when someone knocks on the door. Explaining such complicated policies to the user is pretty challenging. Because of the absence of robust monitoring and enforcement by the platform, the authorization system provides little guarantee that the capabilities requested by an app actually align with the app's description. As a result, despite the existing authorization system for IoT platforms, there can exist a crucial gap between what the user believes an IoT app will do and what the app actually does. Beyond basic overprivilege, where an app requests an unnecessary capability, previous IoT research has studied two additional types of overprivileges: coarse capability and device app binding. In the former, a capability needed to support app functionality also allows unneeded activities. In the latter, a device is implicitly granted additional capabilities that are not needed or intended. The authors have identified an additional type of overprivilege that relates not only to the functionality of the IoT app but also to the user's perception of the app functionality, as seen through the app description. The authors observe that several IoT apps exhibit capability-enabled functional behaviors that are not disclosed to the user, causing a discrepancy between the user's mental model and the actual privilege of the app. The paper refers to this problem as undisclosed privilege. An example of this type is an IoT app that describes the ability to control lights while requesting capabilities to read and control a door lock. Even after a majority of Samsung SmartThings apps were removed from the market due to the previously reported overprivilege issues, we found that 16.7% of the remaining apps still exhibit overprivilege risks. Remote access is also an important security risk, as it enables apps to send sensitive data to and receive commands from third-party servers. In a study, the authors found 27 cases of such behavior, including cases where data was shared without user consent, a clear privacy concern. A smart app's ability to act as a web service expands the attack surface and potentially allows a malicious server to send dangerous commands to an app running on a user's smart device, even though users may not expect such remote control. 17 apps with this behavior were found. Similar to the undisclosed overprivilege, remote access does not match the user's mental model, which illustrates a gap between the current configuration and the approval process. Based on these observations, a general threat in the IoT app landscape is the ability for a malicious or compromised IoT app to steal information from sensors or home appliances or to gain unauthorized access to IoT device functionality. Even if the IoT platform itself is secure and trustworthy, and previous issues of authentication and unprotected communication are patched, such issues with malicious apps may remain, as there can exist a crucial gap between what a user believes an IoT app will do and what the app actually does. Given the unique security challenges of smart home systems, we believe that an authorization system for IoT apps should be designed to achieve the following goals. First one is least privilege. The system should grant only the minimum privileges to an IoT app, just enough to support the desired functionality. Next, it should be IoT specific. Compared with authorization models for mobile devices, which are designed to manage a single device, the authorization system for a smart home framework should meet the needs for multi-device, context-based automatic operations. Permission models based on manifest permissions or runtime prompts, such as those employed in Android or iOS, either do not allow users to make context-based decisions or cannot satisfy real-time demands. Next, it should be usable. The authorization system should be human-centric, minimizing the burden on users while supporting effective authorization decisions. It should also be lightweight. The authorization approach should not inhibit performance with significant overhead. Finally, it should be compatible. The authorization approach should be compatible with existing smart home platforms and applications without breaking the app functionality. In this paper, the authors propose new user-centered authorization and system-level enforcement mechanisms for current and future IoT platforms. The approach, Smart Auth, is designed to minimize the gap between a user's expectations of what an IoT app will do and the app's true functionality. Smart Auth learns about each IoT app's actual functionality by automatically harvesting and analyzing information from sources such as the app source code, code annotations, and capability requests. Because the natural language description developers write to advertise an app in the App Store is the key source of users' expectations for what the app will do, natural language processing or NLP is used to automatically extract capabilities from this description. Smart Auth then compares the app's actual functionality that is determined through code analysis to the functionality developers claim determined through NLP to verify that the requested capabilities and called APIs match the stated functionality, leveraging semantic relations among different concepts and information that correlates them. For example, an annotation indicating a bathroom and the activity take a shower are used to identify the location of the humidity sensor of interest. The Smart Auth system includes 5 components: a program analyzer, a content inspector, consistency checker, an authorization creator, and a policy enforcer. The code analyzer extracts the semantics of an IoT app through program analysis and NLP of app code and annotations, creating a set of privileges that support the app functionality. In parallel, the content inspector performs NLP on the app description to identify the required privileges explained to the user. The consistency checker compares the results of the code analysis and the content inspection to generate security policies and identify discrepancies between what is claimed in the description and what the app actually does and generates a security policy. These policies and information needed to support user decisions are then presented through an authorization interface produced automatically by the authorization creator. The interface is shown in the right picture on the current slide. The verified behavior is the actions that are consistent with the code and the descriptions of the app. The dangerous behavior is something that the description doesn't state explicitly, but the code can potentially do it, which highlights the threat. The resulting policies are then implemented by the policy enforcer based on the user's decision. Now, let us see an example of how Smart Auth works. First step would be to do the program analysis of the source code of the smart home app. I would talk about how we generate the context from the app. For example, the code shown on the slide is from an app that asks the user which device they want to get access to. When we look more closely at the code, we can see that the app wants the user to select the humidity sensor in the bathroom. And now we have the context information for the humidity sensor which is inside the bathroom. We can also see what kind of context trigger what kind of actions. For example, here we can see that when the humidity sensor senses a value that is above the threshold, then the coffee machine is to be turned on. The next step is to do natural language processing and behavioral correlation for the two sets of behaviors. A key goal of a project is revealing any discrepancy between what the app claims to do and what it actually does. To find such discrepancies, we use NLP techniques to extract the security policy from the app's free text description and program analysis to compare it with the security policy extracted from the code. We extract and correlate the behaviors in 3 layers. First, entity, the second one is context and action, and the third one is condition. So the app is indicating that a cup of coffee will be provided after you take a shower. Description analysis tells you that there are 2 entities in this app: coffee machine and shower. Through program analysis, we generated 3 entities: switch, humidity sensor, and let us assume lock. At this point, it is tough to figure out which entity in the program analysis result matches the entity on the description analysis. But if you remember, when we did the program analysis, we did get to know the context. Bathroom maps to humidity sensor and coffee maps to switch. Now we can match coffee machine to a switch and shower to humidity sensor. Let us now decide how to map conditions. Based on the API documentation and description analysis, We can map the taking a shower condition in the description analysis to humidity reading above threshold in the program analysis. The final step is to decide what actions will be taken when the contexts are met. Using description analysis, it can be found that the action is not just turn on the coffee machine, but also unlock the door. It is clear here that unlock the door is an unexpected behavior. It does not make sense that an app that turns on the coffee after taking a shower should also unlock a door. Now that we have the security policy, we can go ahead and generate an interface to display it. While generating the user interface, we need to make sure to match the user's mental model and provide information that matches the user's mental model of the system. The authors conduct an online survey to understand users' mental models related to IoT app installation and the overprivilege problem. The authors try to understand what the users care about when installing smart home apps. The authors use iterative design and parallel studies so that the interface can be improved based on feedback. Then the final smart auth interface was created. If the behaviors are actually related to the functionality of the app, they are shown in green and automatically grants access. And if the behaviors are suspicious, like unlocking the door, it will be displayed in red and access will be blocked. This way we tell the user exactly what kind of behaviors will be expected and which ones are dangerous. The last step is the end-to-end policy enforcement of the authorization. Once a user sets his or her policy settings through the user interface, the policy is enforced end-to-end by blocking unauthorized access. The authors build an end-to-end enforcement of SmartAuth on Samsung Smart Home Cloud so that they can see how the app can interact with the sensors and devices to make sure they follow security policies. The policy enforcement mechanism starts when the user begins to install a smart app. The user is directed to our enhanced interface to set up the relevant devices and policies for the app. This information is transmitted to the policy enforcement module to ensure that the app can only access what the user allows. For evaluations, several experiments were conducted to answer these questions displayed. First, how effective is SmartAuth? This contains two parts. How good is policy extraction? And second, the authors wanted to understand how SmartAuth impacted users' behaviors. Will the users be able to use the SmartAuth interface to avoid unexpected behaviors? The performance overhead and compatibility with existing systems was also evaluated. To evaluate the efficiency of extracting policies, SmartAuth's ability to accurately identify unexpected behaviors was measured. The description and the code of 180 available smart apps was analyzed and compared with the results of the automatic analysis. The authors did not observe any false negatives, although 7 false positives, which accounted for roughly 3.9% of the total, in which smart auth flagged a behavior as unexpected, although the manual analysis of these cases suggested otherwise. The reason for this was that the descriptions were written badly and did not reflect the functionality of the app, so the analysis algorithm could not efficiently map the functionality to the description. A user study was also conducted to analyze how users would react to a smart auth interface. A between subjects user study with 100 participants recruited from across the institutions was performed. The participants were split into two groups. One set of participants will work with the Smart Auth app and the other set of participants will work with the Smart Things interface that is based on the manifests. For each participant, 5 pairs of apps were presented and asked to choose one, and one app among each pair has unrestricted privilege. This example of app pairs are mentioned in the last bullet point. We can see that the apps are really similar in terms of functionality. They are trying to turn the lights off when there is no motion. In the SmartThings interface, visually, we can see that these two apps look exactly the same. Both would like to turn off the lights when no motion is detected. But with the Smart Auth interface, we can clearly see the difference. The second app, that is, the Darken app, has unexpected behaviors. The app can turn the lights off when no motion is detected, but it also accesses the temperature sensor, which is not related to the functionality. So, to conclude, The SmartThings interface does not provide details on what are the expected and unexpected behaviors, but the SmartAuth interface will, so that the user can clearly understand the hidden functionalities of the app, if it has any. From the study, it has been concluded that users who use SmartAuth are better at not selecting overprivileged apps compared to SmartThings. Users who use SmartAuth interface are much better at avoiding unexpected app behaviors as indicated in the dark blue bar on the graph. To evaluate the performance impact and the ease of deployability for SmartAuth, the authors collected all 180 open source smart apps in the Samsung SmartThings marketplace at the time of research. In order to demonstrate that SmartAuth is both lightweight and backward compatible, the authors performed two performance tests. The first one is pre-processing performance, comprising of program analysis, description analysis, behavior correlations, and policy description generation. The second one is runtime performance, comprising of authorization interface generation and policy enforcement. The pre-processing overhead for an app is 10.42 seconds on an average. Since pre-processing is a one-time cost and can be done offline, the authors believe that the performance is reasonable even for wetting a large number of applications. For the runtime performance, the average delay of various functions in the SmartThings platform was plotted. The darker bar in each pair represents the delay in the unmodified platform with virtual devices, while the lighter represents the delay in our customized platform with the additional overhead introduced by SmartAuth. Event handlers incur the highest incremental overhead, while commands incur the highest proportional overhead. SmartAuth incurs an average delay of 35.4 milliseconds, which is small relative to the dominant network latency in cloud-based IoT platforms. In the compatibility tests, the compatibility with existing apps and the behavior of the smart app after enforcing SmartAuth authorization was observed. None of the 180 apps crashed after patching, even with overprivileged security rules enforced. Even after they are patched to remove overprivilege, the 180 apps behave the same as their original versions. In other words, patching does not break the functionalities claimed in the app's description. To summarize, the main goal of SmartAuth is to bridge the semantic gap between what a user sees from the app descriptions and what the app actually does. NLP is used to analyze descriptions and code annotations. Program analysis is used to understand the real code behavior. Then finally, the results from NLP analysis and program code analysis are matched in order to notify users of any unexpected behavior. Through user study, the authors demonstrated that users are more likely to choose a safer app using SmartAuth. The authors are working with Samsung for deploying the SmartAuth interface into SmartThings. This concludes my presentation, and I would like to thank you for viewing it.